Standing in line to see the show tonight, and there's a light on, heavy glow. By the way, I tried to say I'd be there, waiting for Danny the girl is singing songs to me beneath the marquee overload.
Hello everybody, this is your video on local linearity, and we started this idea in class, and I said the phrase local linearity. I had this as the warm-up, and I asked you to predict what the equations of this red, blue, and green function were. Whenever I zoomed out though, they appeared to be lines. However, when I zoomed out, they were definitely not lines. It was a cubic, a sinusoid, and a linear function. So we had three functions, two of which were not lines, but when we zoomed in enough, they all appeared to be lines. And we said that was basically local linearity, but there's a little bit more that we need to talk about here. And I want to start on the graphing calculator here again, and I want to just emphasize a few more things on the calculator as well, some skills that you need to be able to do. So again, we're going to take a function that appears to be, well, what does this appear to be? If you were to look at this blue line and I asked you to make an educated guess about what was graphed here, what kind of function this is, you would probably say this looks like a linear function. It looks like a line. And you can trust the graph. It's drawn to scale. You can trust the grids, the X and Y axis. This appears to be a line because it looks like it has a constant rate of change. However, if you look at the window here, you can see we're really zoomed in here, only -1/2 to 1/2 on the X and 1/4 to a -1/4 on the Y. If I zoom, now make sure you know how to zoom in and out on your calculator. You hit zoom. I'm going to zoom out because I'm pretty zoomed in right now. I'm going to go to zoom out. I'm going to hit enter, but I haven't actually zoomed out yet. You need to put this little blinky wherever you want the focal point to be when you zoom out. I have it at the origin. I'm going to hit enter. Now I'm actually zoomed out. So now it definitely doesn't appear to be a line anymore. At the left and right edges, it looks obviously curvy. I'm going to zoom out one more time. And I'm going to hit enter. You have to hit enter again in order to actually activate it. So this definitely looks like a sine or a cosine wave. And if I go ahead and do zoom, I don't know, let's do zoom standard. You could do zoom trig as well. If I do zoom standard, -10 to 10, definitely looks sinusoidal. And if you go to y equals, you can see I actually did graph sine of x. So it did look like a line. It was actually a function here. So if you zoomed in enough on this graph, it did look like a straight line. And I want to zoom in not just on a graphing calculator, but also on Desmos here, just to show like what the whole idea of local linearity is on a different graph. Ooh, I want this one. So most of the functions and graphs that we're going to be looking at in AP Calculus are not going to be perfectly linear, meaning they're not going to be lines. However, most graphs, I say most because we're going to talk about that at the end of the video, most graphs are nearly linear over a small interval. Now, this here is not a small interval. -8 to 10 is definitely not a small interval. I'm talking like 1.999 and 2. That's a small interval. So if I zoom in enough on these graphs, they should appear to be straight lines. So I'm zooming in. None of them look that straight yet, but we're going to keep zooming in. And one thing that we need to focus on is they need to be smooth curves. And again, I'm going to refer to that again at the end of the video. There can be no sharp points, no jumps, no edges. Only a smooth curve will work. So if you zoom in enough, the graph's going to look linear. Let's go ahead and test that. So let's take this blue function, which is exponential 2 to the x. I'm zooming in on this. Definitely appears to be linear. If I zoom in on my red natural log of x graph and on this rational function here, zoom, 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 definitely looks linear. And you can see like from negative 1.3 to 1.4, let's say, definitely looks like a line there. That is local linearity. Local because it's on a small interval, and linearity because it looks like a line. Okay, so what I want to do is go back to the graphing calculator and show you a skill here that you're going to need to be able to do on this sine graph. And that is drawing a tangent line. You can make your calculator draw a tangent line for you even if you don't have the equation of the tangent line. Okay. Now, before we go ahead and do that, I do want to show you something and have you write a couple things down. All right, so can you pause for a second and jot this down, and then I'll show you the graphing calculator skill. So this is just emphasizing the fact very few graphs are linear everywhere, but most are nearly linear on small intervals. We focused on that. We did focus on smooth and continuous. meaning no sharp points. If you zoom in on a small interval, it looks linear. That's local linearity. So this little visual here will help you. What's what we did in the calculator. And I want you, so make sure you have that jotted down. We are going to go back to this idea at the end of the video, okay? So skip that for now. Here's an important visual. I need to make sure you're all set with tangent versus secant line. A tangent line, and again, we're going to say this so many times this year, a tangent line to the curve touches at a single point. A secant line to the curve touches 2 points in a small area. The tangent line states how fast it's changing at a specific point. It gives you the instantaneous rate of change. I'm abbreviating that. You can write that out if you want. And we're going to approximate the instantaneous rate of change by finding the slope of a secant line. So get those two visuals down. Those are two important ones that we are going to be using when we do local linearity. And I'm going to jump back to the calculator in just a second here. Pause if you need to. All right, so what we're going to have to do, and you'll be doing this within the next week or two in class, you're going to graph your function and you're going to make your calculator draw a tangent line. And I'm interested in x equals 0. I would highly recommend you get your graphing calculator out and do this as well. So go to y equals, put sine of x. I'm zoom standard right now. And I'm going to go to second and hit this program button. Notice above program is draw. Your calculator can draw things like it can draw horizontal lines, vertical lines. Oh, check it out. It can draw a tangent line. Again, even if you don't have the equation of it, it still can draw it for you because it can internally calculate the equation. I'm going to go to tangent. And right now the calculator is waiting for you to put an x value where you want the tangent line drawn. So I'm going to put 0 and I'm going to hit enter. Okay, so that tangent line and that function don't look similar really at all because we're way too zoomed out. So I'm going to go to zoom and I hit zoom in. Let me do that one more time. I hit zoom. I went to zoom in. I hit enter. Nothing has happened because remember, you have to hit enter again to activate the zoom. Looks a little bit better. I'm going to draw a tangent line again. Second, program, meaning draw. Go down to tangent. And enter. I'm going to say, hey, calculator, get me a tangent line at x equals 0. Hit enter. It does it. It looks a little better, like right here where I'm circling right in the middle, around the origin, the tangent line and the function are pretty close to each other, but there's still this big difference. That's all error right there. So let's do it one more time. Zoom in. I'm going to hit enter to activate it. Okay. So this is my function. Now I'm going to go to second, program to draw, and I'm going to go to tangent one last time. Calculator to get me a tangent line at 0, enter. You can barely see a difference here. And you could zoom in one more time and then the tangent line and the function would be basically indistinguishable from one another because we're zoomed in so much on the sine curve. It looks like a line. So you can barely tell it apart from the tangent line. That is the key concept here. When you zoom in enough, the function looks like a line. So then the tangent line will do a good job approximating it because look how close together they are. All right, so here's one last thing that I want you to jot down in terms of visuals. Okay, so we have our tangent line here, and our big goal in this class is going to be to find the equation of a tangent line. However, remember, we need 2 points to find the equation of a tangent line, and a tangent line only hits at 1 point. So what we're going to do is choose 2 points really close together on the function and use it to approximate the tangent line slope. So this secant line slope is going to have a slope that's very, very close to the tangent line because you're going to make these points very, very close together. We'll be using our good old slope formula in order to do that. And remember, the tangent line is the instantaneous rate of change. When you find the slope of that tangent line, that's the instantaneous rate of change. Another thing to keep in mind here is I just did a screenshot of the calculator here. You don't need to write this down if you don't want, or you don't have to draw that, but jot this down. So local linearity is going to allow us to pick any 2 points close together to approximate the instantaneous rate of change. And remember, the original function, which is, I think it was this one. You can hardly tell them apart up there. The original function is going to appear linear. It's going to appear straight because we're zooming in so much. So that means a tangent and secant line can be used to approximate values of that function, which is an idea called linearization. And you might want to jot this word down. We're going to revisit this in Unit 9, this linearization. I'm sorry, in Unit 4. Linearization is what's going to allow us to approximate values like square root of 122 or the square root of 26, or even like, I don't know, cube root of 9, values that are not perfect squares or perfect cubes, but they're very close to perfect squares and perfect cubes. So anyway, local linearity, when you zoom in enough, a function will appear straight. So our tangent line and secant line will approximate values of the function. This is key here. I just want to emphasize when this would not work. I'm going to show you two things here. Can you make a note of these two? And that is this right here. Remember I said we'd go back here. I'm going to give you two vocab words. Well, actually, only really one of them is going to actually be a vocab word here. When would this not work? So like, is there any function that's not locally linear? So what does it mean to not be locally linear? That would mean if you zoom in over and over and over again, the function never appears straight. It doesn't straighten out. So I present to you this green graph, and you might be thinking, this is made up of two straight lines. How could this not be locally linear? And you should recognize this as the square root of x. That's what I graphed right here. And you're right, it is made up of two straight lines. However, a function needs to be locally linear everywhere for you to be able to call it locally linear. So like right here where I'm clicking, you're locally linear. Here, 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 it's straight. Here, 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 the function is straight line. What about, let me try zooming in right down here. So I'm zooming over and over again. Look how small my scale is right now. No matter how much you zoom in, and you can do this on your graphing calculator as well, it doesn't have to be on decimals. No matter how much you zoom in, this thing will never appear to be a straight line. So because the square root of x is not locally linear at 0, you cannot say it's locally linear. Like it fails everywhere. It fails overall. That means that this is not a locally linear function because there's a sharp point. So a sharp point is one place that a function will not be locally linear. Let's take a look at, and I got to zoom out a lot here. Let's take a look at this cubic, x cubed minus 0.8x squared. And you might be thinking, well, this is smooth and curvy. If I zoom in, it'll probably appear straight everywhere. But what I'm going to do is I'm actually going to graph the absolute value of it. So anything that was below the x-axis is now going to be above it. Check it out. Oop. So in blue is the original. In red is everything that was below the x-axis is now positive. So like right here, these are all smooth, curvy areas. When we zoom in, will definitely appear straight. However, let's go over here and whoop, again, not going to appear straight here at 0.8. So because we're not locally linear at 0.8, the function overall is not locally linear. And there's a slight difference here. We're not really going to call this a sharp point because a sharp point technically is whenever you have a straight line and a straight line connecting. Right here, I don't have a straight line and a straight line connecting. I have curvy portions of a graph connecting. This is called a cusp. And let's go ahead and jot that down so you have those words. So functions where it wouldn't work, we have y equals square root of x. That is the most basic example. And the reason that this doesn't work is because we have, so jot this down, we have a sharp point. Anywhere there's a sharp point, not locally linear. And I'm not going to actually write the equation down of that cubic because I did like the absolute value of it. I'm just going to draw an example of a cusp. So a cusp can look like this. So this right here is a cusp. A cusp, you can think of it as like a sharp point with concavity or with curvature around it, I guess. So these were not straight lines, some kind of curving here and here. Another example of a cusp would be something like that, where I'm concave down to concave down. Here I went from concave down to concave up. So anyway, sharp points and cusps, you cannot be locally linear. Pretty much every other function that's continuous and smooth, it'll work. All right, that is all for local linearity. We will use these ideas more in class. Bye.